I didn't have the idea of the interviewing vaccine.
Well, good morning, guys. It is my pleasure to chair our morning session. It is devoted to quantum-like measurements. And we will start with Jacob Denolf from Ghent University. He will speak about first attempt at ordinal projective measurements. Please.
So, hi everyone, I'm Jacob. I'm from Belgium, from Ghent University. And I'd like to talk about ordinal scales and how to model them or try to model them using these quantum techniques that we use here. So maybe some history first. This is actually a continuation of the talk I gave last year in Switzerland, where I presented some work together with Ishmael and Albert. We had this game theoretic model, I'll come back to it later in my talk, where some quantum-like behavior was seen, and we tried to model it in the normal way we model stuff in quantum cognition. And we run into trouble because, like it says, we were shooting 10-dimensional subspaces and 4 25-dimensional subspaces and a 100-dimensional Hilbert space with 60 data points. So from a modeling point of view, this did not work, and we couldn't see why it didn't work because we followed the traditional recipe we use in quantum cognition. So we invented this kind of ad hoc solution by redefining some outcome vectors, and it worked. It was a well-fitting model. Statistically, it did what we wanted it to do, and we submitted this result to this special issue of GMP that's coming up. So that raises the question, this solution that we invented, this ad hoc solution, does it work in other places? Because that would make this story a positive story, like we have something new instead of we have a problem that needs solving. So I'll start with revisiting this famous Squint and Glory example. I won't say much about it, it's been mentioned like in 10 talks already in this conference, I think. It's very well known, there were like 2 measurements. People are asked if they think Clinton is trustworthy, if Gore is trustworthy, and the order in which this question is asked has a significant effect on the outcome. So there's an order effect and a very well-known successful quantum model, which you all know, of course. So from this, I'd like to extrapolate the traditional quantum cognition recipe. Why does it work here? First of all, there's this order effect we see. So we have a reason to assume that some quantum-like behavior is going on. So in the minds that we go to quantum stuff. And we have a low number of outcomes. We only have 2 measurements with each 2 possible outcomes. So it keeps those very small, very easy to fit, statistically speaking. Because if you get more outcomes and more measurements, your degrees of freedom will explode exponentially, which I'll show later. And also, there's no structure between the outcomes that we need to put into our model. It's very symmetric. It's yes or no and yes or no, so that's really easy. We don't need to incorporate anything more difficult into our model. So I want to talk about these two. If something weird happens with those, how can we save our model? Which is what happened with the game theoretic model I made with Ishmael and Albert. So first of all, normally we use PVMs, which is like the traditional projective measurements. So what happens is we have a set of outcomes. They're represented by subspaces in a Hilbert space, and they each have a projector. Quite easy. So outcomes are represented by subspaces. The agent is represented by a normalized state vector in a Hilbert space, and we have 2 rules to calculate stuff. We can calculate probabilities, and we have, and that's the weird thing in quantum mechanics, we have this post-measurement state. And we have this extra restriction in PVM that all our subspaces representing outcomes have to be orthogonal. And the fact that they are orthogonal ensures that when we add all probabilities of all outcomes, we get 1. And that we have repeatability. So if you do 2 measurements, twice the same measurements with no manipulation in between, we get the same outcome. This works quite well in like small examples, because if you have multiple measurements with multiple outcomes, your degrees of freedom, like I said, they explode. If you have 2 measurements with n outcomes and m outcomes, you get n times m dimensions that you need to model this. So if you have like 3 measurements with each 10 outcomes, which is not that far-fetched, you have a 1,000-dimensional Hilbert space, which you can do nothing in from a statistical point of view. Unless, of course, you have reasons to introduce some more structure or some more restrictions, so you lose your degrees of freedom. But then again, if you want to introduce some structure between your outcomes, where would you put it? As, like I said before, as we have subspaces that represent the outcomes, we would need to have some structure between these subspaces. But they should all be orthogonal. Everything is symmetric, so where would the structure be? And this is basically my question to the experts here. Like, I'm going to talk about ordinal scales, which are discrete, but have some ordering in between them, which will become problematic later on. Do they exist in physics, and how do people deal with them? I looked through as much literature as I could, and I never found any example. So maybe that's why we ran into trouble, because people in physics never had any ordinal scales that they should deal with. Well, in psychology, like if you statistic class 2 you have in our psychology department, we talk about ordinal scales and about all these techniques.
So ordinal scales that do not have metric structure.
Yeah, exactly. You just have discrete outcomes and an order, and that's all you have. So no numbers you put on it, no addition, not anything.
Well,
just
the classical example is the scale of hardness. Right? It's the example that S.S. Stevens also invented from physics.
Yeah, but in quantum mechanics, does it exist? Is there any? If anybody knows anyone, please tell me. So okay, this didn't work. So we go like one step beyond, which is POVM. We still have outcomes from a measurement represented by subspaces. We still have our agent represented by a state vector in a Hilbert space. We still have the same rules to calculate probabilities and to calculate the post-measurement state. But we do something there. We don't say that all outcomes should be orthogonal. We just want all projectors to sum to the identity matrix. So we still have that all probabilities sum to 1, but we lose repeatability. This means if we measure something twice, we can, like right after each other, we can get a different outcome. We'll talk more about repeatability later on in this talk. Does this solve something? It does reduce our dimensionality. So that problem is okay. Because why? Because we can press multiple outcomes in a smaller space, because they do not have to be orthogonal to each other. And we can put some structure in the outcomes, but actually less than we expected. I'll show you. For example, if you have this measurement with 2 outcomes, M1 and M2, and we want some structure, so it's not orthogonal, but they're like a bit closer to each other. So we can put some structure in it. We have to have a third vector there, actually in 1 of 4 places. Otherwise it doesn't work. Otherwise we cannot sum to the identity matrix with our projectors, which I'll show now. The projector associated with the first outcome is that one, with the second one that, and if we add those, we get this matrix, and it should be equal to the identity matrix. To get the ones there, that's okay. You just do some scaling, that's easy. But to get the zeros there, you actually have to introduce a third outcome. Which is weird, because maybe in my experiment I do not have a third outcome. So there's not that much structure we can introduce. It's very, very restricted with POVM. So the only solution we saw was we still have this, we still have outcomes represented by subspaces, agents represented by state vector, still the same rules for probability and post-measurement state, but we even lost the restriction that all projectors need to sum to the identity matrix. And we just looked at what happened. It did solve our problems. We could press everything we wanted to press into a smaller space, and we now had freedom to define outcomes subspaces like we wanted to define. Which sound like something negative at first, because if you have too much freedom, like we have this thing in the department, you could fit an elephant. I mean, you just have all these parameters, and of course you have a great statistical fit, but the point is that we could use this freedom to model this internal structure that we have in our experiment. By defining outcomes to be close to each other. This looks a bit more mathematical, but it basically means if you have a certain order in your outcomes, like I, J, K, that you just have vector I, J, I and K, and J has to be in between, which is a very natural way, I think, to represent the order between outcomes. Note that the maximum angle between 2 subspaces is pi over 2, not vectors, but subspaces, is pi over 2. So 2 orthogonal subspaces are like the farthest away they can be from each other. They exclude each other. We'll talk about that later. And this is something nice, because we started from, okay, we need to get rid of our dimensions, which is like this negative reason to try something new, but now we have a positive reason, because we can do something that we couldn't do before. So what did it do? We lost the fact that that sum of probabilities will always equal 1, which is problematic at first. We solved it by defining a scaling factor. So you just calculate your probabilities, they can exceed 1, and then you divide by which you need to divide, which is admittedly not a very elegant solution at all. But then it came to me, if you have problems with some probabilities, then just do not use probabilities. In classical statistics, we have a lot of examples where just odds are used to model stuff. We teach it to our bachelor student, like in logistic regression, you have this formula, and you want to calculate some probability, it doesn't work, so we teach it, don't model the probability, just model the odds behind it. Because odds have less restrictions, they just need to be positive. So then you have this formula for calculating odds, which is quite elegant, it's not that difficult. Because it only depends on PI and not on the other PJ or PK. In the game theoretic model we did this, because we only came up with this a bit later. But this looks more satisfying mathematically to me actually. That seems to work. We also lose repeatability. So when you measure something twice with nothing in between, you can get different outcomes. With PV, when you just use normal projective measurement, it's ensured because when everything is orthogonal and you project on something, all the other outcomes are orthogonal to it. So your probability of obtaining those is 0. With PVMs, it's not. So for a more thorough discussion on the loss of repeatability, I'll just refer to the talk of Kirsty of last year. She did this whole talk just basically about this. And her conclusion was that it's not always necessary and sometimes even not feasible to have repeatability within cognition. But maybe I'll briefly mention how we answer to this concern when making our model. But I'll use the Clinton-Gore example. We had, in the traditional Clinton-Gore example, it's just trustworthy, not trustworthy. Say that you have some ordinal scale that is more complex, which goes from very trustworthy to very untrustworthy. And we claim that this is an unsharp measurement. So basically that when somebody says that he thinks Gore is somewhat untrustworthy, that does not mean that he necessarily disagrees with being quite untrustworthy. Maybe he does in this simple example, but I can imagine if you have 1,000 possible outcomes, that you cannot make any reasonable distinction between outcome 504 and outcome 505. So they do not adhere to repeatability in that sense. So it's, in a way, some sort of incompatible outcomes between, I don't know what these are called in English, but between these. So we cannot reasonably distinguish between different outcomes. However, some outcomes should be distinguishable, like very trustworthy and very untrustworthy. And if two outcomes should exclude each other, then you make them orthogonal. And reasonings like these actually give natural rise to how you should define your new type of base. Two examples where this is used. This is the example I talked about that I did with Usman and Albert. Basically, it was a game theoretical experiment with a sequential prisoner dilemma. You have a first mover and a second mover, and people were asked to play both roles, what they would do. So people were first asked, what would you do as a second mover? Then in some subsample, people were asked, there was a belief elicitation. Basically, people were asked, look around you, you're in a room and there are 9 other people playing this game. How many people do you think have cooperated here? People replied to it and then were asked to do their first move. And if this was done, the first move cooperation rate actually doubles. Which seems like me, like quantum-like behavior. So here we have 2 different outcomes. Here's 10. To model this effect, we need a 10-dimensional Hilbert space. Here, 10-dimensional Hilbert space. These were considered compatible, so together it's a 100-dimensional Hilbert space, which did not work. So we solved it like this. We redefined our belief outcome space like this, not something 10-dimensional, but something 2-dimensional. These are equidistant. We still use the rules to calculate probability and to calculate your post-measurement state like you would do otherwise. And this actually makes, which is quite nice, this belief construction that you do, it makes it a rotation, which is exactly what Potters and Busemeyer did in their prisoner dilemma treatment. But we explicitly elicit these beliefs and explicitly have probabilities that we calculate.
Did you follow their paradigm exactly? Or? or not?
Yeah, we knew about it, and we didn't start with it, but then we did this, and then all of a sudden we thought, yeah, this looks exactly like it.
Yeah, but I mean, the experiment, was it the same type of experiment?
No, not really, because it's a sequential prisoner dilemma.
But in each part, was it the same steps? In each part of the sequence, was it the same as?
Yeah, just a traditional prisoner dilemma.
Were the instructions the same?
In our experiment or the Potters and Busenmeyer experiment?
Were your instructions the same as their instructions?
I don't know, I didn't do the experiment, but I guess it was very comparable.
The instruction to, consider what the other 10 people in the room did
It's different.
is different.
Yeah. But in the Potters and Busenmeyer model, they assume that we construct some beliefs, and that's a Hamiltonian approach to state vector,
I
which we do
understand-
as well.
I understand the model is the same.
We were just happy that all of a sudden it looked like what they did. And it worked. It had a very nice statistical fit. Now we need to mention something that James Yearsley told us, that, like I mentioned before, when I talked about POVMs, when I have these two vectors, I need this third one to make it work. You can do it here, that's what he suggested. He suggested an 11th fictional outcome, which would be somewhere here, which ensures that we have a POVM and not something else. And he says that would mean the measurement has failed, let's redo it. So you would redo it and recalculate probabilities and sum across it. And that would have this identically the same statistical results. However, we also have it in our paper. I don't find it satisfying. You have this fictional outcome. I mean, our measurement couldn't fail. All people replied, it never happened. So if you don't agree with loosening the POVM restrictions, actually you can get the same statistical results by having this fictional new outcome. It works. Then maybe another application to show that you can actually use the structure from the theory to get to this new base. If you have a Likert scale, which are widely used everywhere in psychology, from strongly agree to strongly disagree, it's ordinal, which is what I want. It's balanced, which means that the distance between all outcomes, between all following outcomes is the same. And it's symmetric, so neutral is always in the middle, and you have the same number on each side. First I mentioned Campara has done some quantum-like Likert scales, and they always put the ordinal structure in the state vector of the density matrix, which to me is a bit cheating, because that talks about the agent and not about the outcomes. So suppose that you think that strongly agree neutral and strongly disagree should exclude each other. These are very distinct opinions, and you use the idea that it's balanced and symmetric. Then you naturally have a structure that looks like this. It follows automatically from the theory behind it. And now maybe I can show why I think that putting the structure in the state vector is a bit cheating, because if you do it like this, our agent can still be in a superposition between just outcome 1, which is strongly agree, and outcome 5, which is strongly disagree. Maybe he only likes very extreme opinions. Well, if you would put some structure in the state vector, it would be like, I don't know, maybe something like this. Like only state vectors, A, B, A, and then some zeros afterwards. So you have like only groups. So here it would be impossible to be in a superposition between outcome 1 and outcome 5. So our approach is not put any restrictions on what the agent itself might think. I haven't tried this with any data yet, just to show that you can build this new type of base just coming from the theory, which is something nice. So yeah, in conclusion, we loosened some PVM restrictions and even some POVM restrictions to incorporate structure in our outcomes, while reducing dimensionality, which was problematic in our setting. The nice thing is that this allows for even empirical testings and making predictions of structure and outcomes, and not just in the agent. There are two major consequences. There's also repeatability, and you need to do some tricks to get your probabilities to do what they want. And so far, there's only one successful application, which was the game theoretic model I talked about. So please give me any feedback you have before I put this in my video. But thanks for your attention.
Thank you.
far apart, is there some justification of thinking that rather than being opposite of one another, they're orthogonal? We use when you have judgments like strongly agree
Yeah.
and neutral, and you say, well, these are sufficiently far apart,
Yeah.
and you put them in an orthogonal relationship.
That's the furthest apart they can be.
Yeah, that's the far apart. How? And what happens if you have neutral and strongly disagree? They're in an orthogonal relationship, and strongly agree and disagree. And strongly and disagree. How?
I think
You keep adding dimensions when you do this.
Yeah, yeah.
Right? But it seems that strongly agree and disagree is further apart than strongly agree and neutral.
Yeah, that could be the case, but in Likert scaling, it's assumed that it's balanced and symmetric. And I think what you said is not balanced and symmetric. But you could do that, sure. But that wouldn't lead to this.
Wouldn't lead to that one. Yeah, I just wonder what the justification.
Yeah, just from literature about Likert scaling. So that's a nice thing, that you have your literature study and you let your structure come out of your psychological ideas. But you could do it.
And if you were to ask the questions negatively rather than positively, you would get you scale on the same way.
Yeah, I think so, because I have vectors here. It's actually about subspaces. So if you do this with your vector, it doesn't actually make any difference.
But experimentally, doesn't it?
Yeah, it would. But that's because people react differently to the framing. So that effect would be somewhere in the state vector, I think, not in the outcome.
Okay, good.
So that's nice. We can distinguish between these
Okay,
two.
I understand that. Good distinction.
Any more questions?
I could just, since you asked for comments, just one possible consideration for you, that by doing it, by modeling closeness by simply angles in you know, of the vectors within a given dimensionality, let's say 2 or whatever. You're coming very, very close now to classical way it has always been done in psychology. You know, the Thursdonian scaling is a continuous scaling on a simple line, and in multidimensional scaling, you know, it was very common to represent stimuli by vectors and to model the closeness by the cosine of the angle between them. So I guess what you might be interested in is while you proceed along this road, which may very well be promising, you probably should look at whether this quantum part of it becomes kind of an unnecessary baggage that you can dispense with and achieve exactly the same results.
But then we would lose the order effect that we wanted. I mean, we started from the fact that if you should believe in a situation that this changes completely, there's a very clear order effect in the data.
You know, it is one of the greatest misconceptions in the area of quantum cognition that order effect in some way cannot be handled by classical probability. It is such a crude mistake that I hope that, you know, people will stop making it. Yeah, I mean, order effect is completely compatible with the classical thinking, classical probability, so by itself it has nothing to do with quantum things. So that should not be an argument. The argument may be simply that, you know, when you do it in a classical way, you know, your fit is worse than when you do it in this quantum way, or maybe you have some metaphysical argument in favor of that. All I'm saying now, and I'm not criticizing, you know, in fact I was one of the reviewers of your contributions to it. I gave it a green, so it's nice. It is perhaps very promising. But this consideration, how necessary it is, because sometimes people do things by inertia. They have done it in a quantum way, and now I'm also doing it in a quantum way, and I'm modifying it and expanding it, whatever. But by doing that, you can come so close to a classical way that perhaps this quantum things becomes unnecessary. So the burden of proof is on you, right? To convince us that it is still quantum in some essential sense of the word. Okay.
We are such a nice community, so I think it's just the pleasure of being in it. You can be motivated to keep something quantum in your models. So let's thank the speaker again. Our second talk is called Eigenlogic, a quantum view for multiple valued and fuzzy systems. And it is presented by Zeno Toffano. It's a joint talk with François Dubois. So please.
Thank you very much. So I will present you work which I did in collaboration with François Dubois, who is not here. He was one of the organizers of Quantum Interaction in 2012. And so just to see what are François Dubois is from CNAM and Professor of Mathematics, also Department of Mathematics at University Paris-Sud Orsay. And I am at Telecom Department Centrale Supérieure, which is a Grande École engineering school in France, and also Laboratory of Signal and System in CNRS. Okay, so I'm a physicist, so I'm more familiar with electrons and things which are physics. So I will talk about logic. So I hope you'll be indulgent, because perhaps some things will appear naive. But the idea is to do something operational at the end. The idea is to get some results which perhaps could be useful. So I start by giving the context around quantum logic, and starting with the experiment, the very known experiment, which is the double slit experiment, and seeing that this double slit experiment is one of the reasons why actually classical logic is not considered for quantum physics. For example, if you take three proposition A is the electron is detected at point X, proposition B, the electron went through slit 1, proposition C, the electron went through slit 2, and if we do this in a propositional way of logic, we see that the distributivity is not verified by this experiment, because if we take the union, then we will have interference, but if we separate the events, then interference disappears. So this is a picture from a very famous book of Richard Feynman. I think people in physics know this. And so the peculiar feature of quantum mechanics is the possible non-commutativity of observables in the experiments. Now, this has motivated research on more adaptive logical systems, and of course, seminal work of Kirchhoff von Neumann, which replaces Boolean algebra with lattice of closed subspaces of finite Hilbert space. Now, quantum logic is where quite now it's 20, 30 years, which is very active, but it has some detractors as promoters, and one problem is that it is not considered as the operational tool, mostly for emerging quantum information and computing technology. So there's much debate, and just a provocative, controversial conjecture. I read this in the book, I will say the author afterwards. Imagine foundations, if not quantum, at least in a quantum spirit, something of the sort Alan Kohns, the field medals, is doing with non-commutative geometry, that is the project of the day, enough to be kept busy for a while, which helps to revise the user relation logic quantum. Instead of interpreting quantum in logic, one tries the opposite. So perhaps one should, instead of adapting physics to logics to try to do the opposite, logics to physics. So this is very general statement and made by Jean-Yves Girard, which is a famous logician. He's the founder of linear logic, which is the follower of lambda calculus of Church. So he has a very sharp opinion about quantum logic. He's not against quantum, he's more or less against quantum logic. But this is his opinion. Okay, so the context is this, and another context which will be in my talk, is the multivalued and fuzzy logic. Quantum physics and modern theory of many-valued logic were born nearly simultaneously in the years 20 and 30s, and due to the two first founders, we can say it's Emil Post, we'll come later on him, and Łukasiewicz, the Polish school of logic, which was very, very active on multivalued logic. But then this trend disappeared a little bit because actually no real application were found. And recently, there's a revival of interest in applying many-valued logic to the description of quantum phenomenon. And this is also connected to the rapidly developing branch of fuzzy set theory. So fuzzy sets are in relation to infinite valued logic as traditional sets to classical two-valued logic. So we can say that perhaps many-valued logics are becoming again a trend, and we'll see that also for quantum computing, they are becoming important. Now, the fuzziness of logic could be interpreted by the probabilistic nature of quantum measurement, the Born rule, for a projective observable A measured in the context of a quantum state C. We have this relation. The probability can be the mean value of the projective observable, and this is actually what is called the Gleason theorem. So this has been proved. So we can have these kind of rules, and an interpretation of quantum mechanics could also be based on many-valued logic using adaptive operators. This is one of the attempts of this work. Now, we start with history. So, George Boole, why George Boole? Well, actually, it's very interesting to see how George Boole gave a mathematical symbolism to the numbers 0 and 1, representing respectively false and true of character of proposition. So the very famous book of 1847 and then 1854. Now, what is interesting is algebra used by Boole was not what is today considered Boolean algebra. But it is an arithmetic form using idempotent symbols. This is quoted and also confirmed by many researchers, and one of them is Theodor Halperin, who made a quite funny title article, Boole's algebra isn't Boolean algebra. Now, what did George Boole do? He actually used symbols, and which he then called elective symbols, which had the property of idempotence. And this is represented by x squared and x, which can also be written as x times I know 1 minus x equal to 0. So what is the property of this? Well, this equation is only verified by 0 and 1. That is why you have to choose 0 and 1. Now, this equation was considered by Boole the fundamental law of thought. He writes this in the book in 1854. Now, Boole's approach was operational because x, the symbol x, acts as a selection operator. So George Boole named these elective. Elective and selective, I think, can be considered the same. As will be emphasized in this work, the algebra of elective symbol can also be interpreted as an algebra of commuting projection operators and used for developing propositional logic in a linear algebra framework. So this paper you can find on archive, which is more on Boole's work. Now, history, again, truth tables. Now, truth tables are known to everyone, but we can see that there was not trivial how they came out. So this is an excerpt from the book of Karl Menger, who was a member of the Vienna Circle, and he quotes that truth tables were introduced by Charles Sanders Peirce in 1880, but attracted little attention. Then truth tables were rediscovered and tautologies discovered simultaneously and independently by Emil Post, again, in a very, very interesting paper, a fundamental paper, which is the paper of 1921, and by Ludwig Wittgenstein, very famous too, in his famous Tractatus Logicus Philosophicus, 1918, and this is the first complete formulation of truth tables for 16 elementary propositions of 2 atomic propositions. This is the thing you find in Tractatus. So Wittgenstein, Post were the first who systematized the structure, because they said this is the complete structure of a logical connective, in this case for 2 atomic propositions. So we will use truth tables. This is why I presented this historical view. Now, let's start with some logic. This is what you call arithmetic binary logic. It's used by researchers who work in logic synthesis. And it means we just do algebra, arithmetic algebra. So we use the Lorentz-Loh rule, x squared dot x equal to x. X is complete with its complement. And then we want to find functions which are functions of these symbols and which enjoy the same property of identity. Now, and this is also quoted in George Boole, if the functions of this elective symbol are also elective, then these functions are interpretable in logic. Now, in general, we can consider finite number n, cardinality, functions going from codomain to dimension 2, and for a single value n equal to 1. If we consider 2 values of this function in 0 and 1, we have this unique development which gives the unique form of developing an elective function of the symbol. So this form here was derived by George Boole. He had some sort of demonstration. It can be derived from Taylor expansion. But this is a unique form. And it means that any functions of this kind can be developed on 2 basic functions, y minus x and x, which are actually projectors. Now, f0 and f1 are the truth values of the development. So the factors are truth values. And for example, if we take a 2-argument function, we have the same rule. And this was very clear for George Boole. We just do it automatically this way. So it's straightforward to write this. The number of different connectives is 2 over 2 power n. This is a combinatorial number. If you take n equal to 2, we have 16 connectives. So we get all the logical connectives in this way. And this here is the table where we have the logical connective, the truth table, and the arithmetic expression. So these arithmetic expressions will be used in our quantum approach, and particularly the last column. So we can recognize here, for example, the OR, which we had before, which is here in distributional logic, meaning that x plus y minus x is the OR function in this kind. So what is particular is that you can use minus sign, and we are not in a Boolean algebra, meaning we don't have modulo addition. This is real addition and real subtraction. So this is quite interesting because we will see it will work very fine. Now, what is the motivation of this research? So we say that a projector in Hilbert space can be associated to a propositional logical system. This operator, being a mission, has the characteristics of quantum observable and can thus be defined as a logical observer. The view of eigenlogic is the following. This is thanks to a reviewer. I don't know who he was. He gave us this kind of schema. Eigenvectors in Hilbert space are atomic, could be associated with atomic propositional cases. Projectors are logical connectives. Eigenvalues are truth values. Now, it came up that this idea is almost the same as what is now called recently quantum predicate, which is due to a very recent book on foundation of quantum programming. And in classical logic, predicates are used to describe properties in individual systems. Then what is a quantum predicate? A natural idea is that a quantum predicate should be a physical observer. Historical Dirkhoff von Neumann quantum logic is the first logic for reasoning about the properties of quantum systems. One of its basic ideas is that the proposition about a quantum system can be modeled by a closed subspace X of the system state's Hilbert space. This subspace can be seen as the eigenspace of projection of Px, corresponding to the eigenvalue 1. And the eigenvalue 1 can be understood as the truth value of proposition modeled by X. So it's quite natural. Just to go back in history again, John von Neumann considered projectors as proposition. And if you look at his book of 1932, he quotes exactly this sentence here. To each property, I don't know how to read this symbol, we can assign a quantity which we define as follows. Each measurement which distinguishes between the presence or absence is considered as a measurement of this quantity, such that its value is 1 if it's verified and 0 in the opposite case. This quantity, which corresponds to the symbol, will also be denoted by the same symbol. So it was quite clear also to von Neumann, before his paper about quantum logic, that projectors could be modeled in this way. And to finish a little bit this math point of view, we have to cite also Marshall Harvey Stone, which was quoted in the book by von Neumann, which establishes that parallel between operations on projectors and commutativity. For example, it says this: E1, E2 is a projection if and only if E2 equal 1 equal to E1 equal 2, meaning they have to commute. And then he gives also the relation of addition and subtraction. So, meaning that it was quite clear at that period that we could actually work with these projectors, and von Neumann, of course, introduced also the density matrix as a rank 1 projector. So this is a little bit the way we will proceed. Now, let's proceed with the operators. So we introduce what we call a seed projector, which is just a very simple rank 1 projector in 2 dimensions, which will be defined by the state 1. Of course, it's idempotent. And what is the expected result when applying this projector onto its eigenvector 1? Of course, it's 1 times 1, so the eigenvalue is 1. The same you can do with the complement on 0, then we get 0. And so the eigenvalues are real, the operators are observable, and the action of P can be interpreted as a logical proposition about the belonging or not to the subspace associated to the projector P. The value 1 indicating the belonging. So this is very simple. So we define this P-seed projector, P1. We can define its complement. And if we represent it in a vector, in a matrix form, it's very simple. We have column vectors, and then we have matrices. And of course, we verify completeness. So this is standard quantum physics and linear algebras. Now, how can we do development for these logical observables? Now, we will really do the same thing as was done by George Boole. So we will develop on rank 1 projectors. So we just write that a logical observable is nothing else than the truth values times the corresponding rank 1 projector. And we can get, here in this case, a 2 times 2 matrix. F0 and 1 are the eigenvalues and correspond to the truth values. So this allows to generate, for example, the 4-1 argument logical observables, which are trivially P1 minus P0 and identity. Now, the 2-argument logical observables is made in the same way as for rank 1 projector. We just define now rank 1 projectors in 4 dimensions. So we have exactly the same way of doing things, and in matrix form would be this one. So let's do the analogy full analogy pools. Now we will define what we call logical projectors. So logical projector in logic means that when you apply the logical projector, you get one of the true values of the proposition. And we will use Kronecker product. Now, there are some properties of Kronecker product that have to be reminded. First of all, the Kronecker product of two projectors is always a projector. And second, if projectors are rank 1 projectors, the Kronecker product is also a rank 1 projector. And you have this rule here, which is the quite nice rule of Kronecker product. You get many special effects in quantum physics, that when you have 4 operators, you have this rule of interchanging the matrix product with the Kronecker product. So we do this to find the projectors, and we have 4 projectors in this way here. Just doing a Kronecker product with all the combinations between the seed and the complement. So the logical projector F for 2 argument cases will be written this way. A will be P Kronecker projector identity, and B will be identity Kronecker projector. So the AND conjunction, for example, becomes very simple. It's just a product AB, as for George Boole. And because of the rule of the Kronecker product, it's P Kronecker P. So then we have the complement. And so it's very easy to do this kind of math. Now, just to see that George Boole did 0, 1, we can go to -1 plus 1 minus 1. This is what you call Fourier transform of Boolean function. So I will go very fast. It's now a domain which is known mostly for cryptology. People do very many things in this field here. So we can define things in plus minus 1 instead of doing 0, 1. And we get this relation here. There's an observable G, which is 1 minus 2f, which actually gives you values plus minus 1. And we have the same kind of procedure, and we have a C projector, which is Z, which is 1 minus P, 2P, and it becomes actually the Pauli matrix Z. So meaning that we have almost the same, operator as spin, if we do logic in plus minus 1. This has been also done in some recent work, which you call Fourier transform of Boolean functions, quantum Boolean functions. So we can define some functions XOR and CZ in the same way. We do the same rule. They are now called dictators. This is named not to confound with what you call logical projectors. The name is dictators. And for example, XOR is this function. And interesting is AND. AND becomes a little bit more complicated, but what is interesting is actually the control Z function in quantum for quantum information. So these are all the functions, for example, in 0, 1 and plus minus 1. So you get, for each connective, you get observable. These are 4 times 4 matrices. We could do it for 3, we could increase. It's no problem. So just let's finish with 2 topics. I hope perhaps one I do it quite fast, but I try to do it. Now, what I talked up to now was we worked in the eigenspace. Now, what happens if the state considered is not an eigenstate of the system? Well, it's standard quantum mechanics. We say, okay, we have 4 eigenstates, and then we can always put the state as a linear combination of the 4 eigenstates. So what is interpretation? If only one of the coefficients is non-zero, then we're back in the deterministic case, determine deterministic atomic proposition. But when more than one coefficient is not 0, then we are in a fuzzy proposition. Meaning fuzzy, meaning that the truth value can be between 0 and 1. Not completely false, not completely true. So this can also be done in a very standard way with quantum mechanics. We can calculate fuzzy membership function. So we just consider generic quantum state, very general, so angles, alpha and beta, and we do Born rule, we calculate mean values, so we get cos square alpha, and then we do the complement, which is 1 minus the mean value, and this is one of the requirements for fuzzy logic, meaning that to have the complement. So, and this can be interpreted as a probability. So, we can do this things for combined quantum states. We take this is a 2-qubit system, which is represented by a Bloch sphere. Each state can be defined by an angle, and we can do the same thing, just doing the average. Now we use the 2-argument observables. For example, we calculate the mean value for A, we get probability P, B, we get probability Q, P and Q being the square of cosinus of the angles. And then we can, in the same way, get conjunction and disjunction in this way. So we get, for example, here, we have the formula for the conjunction with probabilities, with the minus sign. So this was reported in a recent paper by Thomas when he left, but they found the same thing. So what happens if you have entangled state? Well, entangled state, in general, one can show this result, that the mean value of whatever logical observable for entangled state is always smaller or less than 1. It's very easy to show, and this is also some way Gleason's theorem. So, okay, so I hope I have, in 2 minutes I will finish. So we do the last step. We have many things done. Multivalued logic. Now, okay, this is used mostly is used for computer science in some languages. Okay, past this. What is different multivalued logic? And the number of connectives are m power n. So it's very, very huge numbers. For example, if you take one argument, you have 27 connectives. In 2 for 2, we have 4. And if you take 3, you have 19,683. So it's very huge. I don't know if you can really do much reasoning, but we'll see 2 examples. Now, what is important, I think, for physics is that we can identify this with one of the very important quantities of quantum physics, which is angular momentum. So angular momentum is one of the observables for atoms, molecules, and it's characterized by 2 eigenvalues, which are the total angular momentum J and the magnetic angular momentum J, and there's rules. J must be integer or half integer. This means the bosons and fermions. And Nj is variable between minus J and plus J by step of 1. So, for example, an orbital momentum here, I think this was number 2, 3, would be give this. The simplest case is spin, where you have plus minus 1. And we will see that we use orbital angular momentum with equal to 1, and there we have plus 1, 0, minus 1. This will be here. And the observable is this. This is the observable for angular momentum. So we have the diagonal plus 1, 0, minus 1. Now, we do the same trick as we did before. The eigenvalues plus 0, minus 1 are our logical values. We can adopt this convention. False is 1. Neutral is 0, true is minus 1. Then we define the rank 1 projectors, which are here. We use the seed, which is this one, and we do the developments. So one example, you have the same kind of rule. You can always define the dictators in the same way. Now these are 9 times 9 dimensional matrices. And for example, we looked one example. The examples which are quite used in multivalued logic are mean and max. These are the tables. We get these expressions, and to verify that this is in some way consistent, we say that binary logic must include ternary logic by eliminating the neutral state, and we come back to the expressions we had before. So we can go very, very much higher with this. So now I conclude. And conclusion will be observational interpretation. We have presented an operational formalism named eigenlogic using quantum observer in Hilbert space. The idea is that eigenvalues are logical. The eigenvalues of a logical observer are truth values. The associated eigenvectors are atomic proposition, the results of a measure observational logical observer, which gives a truth value. Now it becomes interpretable when the observation is made in the eigenspace of the corresponding logical observable, and if observations are made outside of the eigenspace, then we are in the quantum average. We can have probabilities, and I think this gives a natural analogy to the measurement postulate of quantum mechanics, because this notion of interpretability is that actually you can only have the eigenvalues, but meaning that this is logical. You can only have the logical values, so you can only have consistent logical values for this. So this is all. You can read it perhaps by yourself. There's some application which could be interesting is algorithmic approaches in vector space of high dimension. Of course, the dimension can explode, but you could use logical reduction tools. It is also important for physics because we see that, for example, the angular momentum are really the logical observables. It's not just analogy; they are. So we could work with these. So, for example, we could think of quantum gates working in this way. And for example, quantum interaction, that could be interesting. For example, in quantum cognition, I made a reference, but also in distributional semantics with matrix approaches like LSA and this kind of. So thank you very much. I was a bit speed because I want questions and critics because it's quite new, and so what I need is reactions, and well, okay, you can send me.
Why Boole called fundamental law of thought?
In his second book, he writes this in some place, and because he really thinks that this action of elective is the way we think.
Why?
Because, for example, he says that when I take, well, for example, you have repetibility. When you say once the question, then you say the second time the question, you don't get more information.
Well, I did it right now when I asked again.
No, but this, and his opinion also was that, for example, he gives this example. He says, I have one proposition x and one proposition y. If they're equal, then he says x equal to x. And then he says, I can do this more and more times, then I have x squared equal to x. And for him, he was convinced of this. So I don't know why exactly, but it's really written in his book. It's not something which is, he believed it was really his, I think this motivated also his choice of 0-1. It wasn't.
Okay, so let's.
I wanted to ask about the connection of this construction and quantum logical gates in quantum computing. For example, is there a connection between this and other gates like Toffoli gates?
I work on this in this moment. It's quite difficult, but what I see in my intuition is that quantum gates are proposed nowadays. Most of them are control gates, and this is a paradigm of David Deutsch, who said quantum gates must be like this. What I tried to do with some students is, could we do the same calculation with these kinds of gates? Because it's logic, so we could do adders, we could do something, we can do. So it's more or less, for example, the control not gate becomes the AND gate by changing the basis. But the function is not the same, of course. So you cannot say that these two functions are the same. But because people in quantum information always use linear transformation and all that, we could do some quantum computing in this way. I think it's not a big problem.
Could you use these operators as a universal set of gates?
Yes, I think.
Could you generate?
No, yes, because and negation are universals. So for logic, they are universal. Emil Post showed that for multi-valued logic, permutation and majority are universal.
Yeah, but in the quantum case.
Yeah, also, yeah, because for the projectors. Meaning that from these two, you generate all the other ones. So this is a demonstrator from the mathematical point of view.
Okay, so,
So thank you very much.
Thank the speaker again. And we are moving to the last talk of this morning session. It's Kevin Dunne, who's going to talk to us about the new perspective on observables in the category of relations. Please.
Thanks. So it's great to be here. And so my claim here is I'm going to give you a new perspective on observables in the category of relation. It has occurred to me that lots of you won't exactly have an old perspective on observables in the category of relations, so maybe this seems a bit obscure. So what this work really is I'm trying to bridge a gap between two very recent and novel approaches to quantum mechanics. And what these have in common is they both use the language of category theory. So category theory is a branch of math which is very abstract and famous for being obscure and difficult. But quantum mechanics is also abstract and obscure and difficult, so this should be the perfect match, right? So I'm going to give you a brief kind of overview of these two approaches and try to bridge some kind of gap between them. So the first one is goes to this paper by Samson Abramsky and Bob Kuka, and it's using the structure of monoidal categories to talk about quantum mechanics. So their idea here is that quantum mechanics isn't about Hilbert spaces. There's all this stuff with Hilbert spaces that we don't really need, so they strip all the unnecessary details away, leaving behind just this underlying categorical structure, and you can recreate a lot of quantum mechanics using only that structure. And the second approach I'm going to talk about is this topos approach, which goes back to Chris Eisham and Dorian, and also Bottomfield as well. And so here they're using this topos theory, which is a part of category theory that's a very powerful tool. And it goes back to this paper where they say what is a thing, and in this paper they have this quote by Heidegger. So from the range of basic questions of metaphysics we shall ask here is one question: what is a thing? And so they're really trying to get to grips with the foundational issues of quantum mechanics, which are still unresolved. And so they're going to use topos theory to attack that. Now, even the definition of a topos is pretty involved, so I'm not even going to go there. We're going to see a little bit about what they do. So these two approaches are really very different. They use very different kinds of mathematics, and they're also interested in different questions. They're really trying to do different things. So they're not secretly the same thing. That's not what I'm getting at. But there should be some way to kind of translate the language of one into the other and move between them. So how are we going to do that? Well, on the one hand, we've got the monoidal approach and the topos approach, and we're going to think, what does it mean to be an observable if you live in the universe of monoidal categories, and how do we imagine observables if we're in topos theory? And we're going to try to build a link between these two, kind of using observables as a bridge. So we'll get into monoidal categories. So a strict symmetric monoidal category is a category, so it has objects, which you can think of as like some type of thing, and then morphisms between objects, which you can think of like a process. So a morphism F from A to B is like a process that takes things of type A and creates things of type B. And we also have a monoidal product, so this lets you, if you have two objects, you can take their monoidal product, and this gives you a new object. And if you have two morphisms, you can take their monoidal product, and that gives you morphisms. So if you think of these as processes, if I've got a process F and a process G, well, the output of F matches with the input of G, so I can plug them together sequentially. And then I can also compose things in parallel, doing them side by side using the monoidal products. So if I have this process F and process H, I can do them kind of simultaneously using the monoidal structure. So you think of these as kind of abstract processes. And we also have the monoidal unit, is this object in the category where when I take the monoidal product with the unit, it doesn't change. So it's like the unit of a monoid or a group. And so I'm going to want a bit more structure on my symmetric monoidal categories. In particular, I want a dagger. So this is a certain type of functor. So if you like these words, then you can think of that. Or you can just think that every morphism has an adjoint. Okay, so any morphism F from A to B, I can specify a new morphism from B to A that sits. It's a kind of formal adjoint. And I'm going to ask that if you take the adjoint twice, you get back the thing you started with. Okay, so we can think of the fundamental example of a category like this is the category of Hilbert spaces. So our objects are Hilbert spaces, the morphisms are bounded linear maps. Take the monodal product to be the usual tensor product. The monodal unit is the ground scalars C, so if you take the tensor product of these scalars with a Hilbert space, that doesn't change the Hilbert space. And the dagger is the usual Hermitian adjoint that I'm sure people are familiar with. And so the claim is that of Abramsky and Kuka is that you can recover a lot of quantum mechanics just using this structure of monoidal categories. And with that in mind, we can look at other examples which are not category Hilbert spaces, and so the famous one is category relations. And so here your objects are just sets, the morphisms are relations between sets, your monodal product is the usual Cartesian product, the monodal unit is the singleton, so if you take the Cartesian product of a set with a one-element set, this doesn't change the set. And the adjoint you can define in a reasonable way. So if I have a relation F, then I'm going to define this relation F dagger in the way that F dagger relates a Y to an X if F related that X to the Y. So it's just a straight kind of reversing. And so we can start to talk about ideas from quantum mechanics in this now new setting and see what happens and see kind of compare things. And just as a kind of a remark, this Hom set, so this notation Hom means all the morphisms in the category from X to Y. So in this case, all the relations from X to Y. And in category relations, this has a natural partial order. You just take subsets of relations. So when you have monoidal categories, you're generally interested in the algebraic structures which live in those monoidal categories. And in categorical quantum mechanics, we're particularly interested in Frobenius algebras, in particular dagger special commutative Frobenius algebras. But when I say Frobenius algebra, I mean dagger special commutative Frobenius algebra. So what is a Frobenius algebra? Well, it consists of some object, and then you have a multiplication map. So this is an algebra map that takes two copies of the object to one. And then we're also going to think about the adjoint of that multiplication map. So this is a co-algebra map, which takes one thing to two. And then being a Frobenius algebra means you satisfy a whole bunch of equations, but I'm not going to show you what those equations are because they don't really matter. But what we will do is look at an example. So I'm picking my monoidal category to be the finite dimensional Hilbert spaces. And I'm going to pick an orthonormal basis, given by these E's. And I'm going to define the algebra as follows on this basis. So it's easiest to see what the co-algebra does. The co-algebra copies these basis elements, and then we extend this linearly to the whole space. And when we're looking at this, it's only the basis elements that get perfectly copied by this map. This map doesn't copy arbitrary things, it only copies this specified basis. And then the multiplication map does the obvious thing there. Okay, so why do I care about this? Well, it's a result from this paper by these authors that every Frobenius algebra in finite dimensional Hilbert spaces is of this form. So there's a one-to-one correspondence between orthonormal bases of a Hilbert space and one of these Frobenius algebras that you can put on. So we think of an orthonormal basis. What's this got to do with observables? If you have you think of the eigenbasis of a non-degenerate self-adjoint operator. This always gives you an orthonormal basis, and so I can think of the orthonormal basis as being the outcomes of a measurement. And so this Frobenius algebra kind of captures the outcomes of a particular measurement. So I'm thinking of, I want to encode ideas of observables as these Frobenius algebras. And again, you might be thinking, why? Well, I think this is a quote from that paper. So hence, orthogonal and orthonormal bases can be axiomatized in terms of composition of operations and tensor products only. So ideas like basis and orthogonality, these are very specific to the category of Hilbert spaces or categories where the objects are like vector spaces. But these Frobenius algebras, I can think of these in any monoidal category. So it's a much more abstract idea. It's a much more abstract way to encode this idea, which gives us a much wider way to think about it. So this is the kind of motivation. And so in particular, when we're thinking about these Frobenius algebras in finite dimensional Hilbert spaces, it was these basis elements which were copied by this map. And in general, these elements which are copied by a Frobenius algebra are called the set-like elements. And so these kind of corresponds to the eigenvectors. So it's the set-like elements we kind of think of, these are like the individual measurement outcomes. But in other categories, these set-like elements will maybe look quite weird or not even exist. And so if we think of Frobenius algebras as encoding information about observables, well, we can now look at them in other monoidal categories and see what happens there. And so Dishko-Pavlovich characterized all the Frobenius algebras in REL. And so the Frobenius algebra in REL is, you have this algebra map defined on some set, and he figured out that this is actually, if it satisfies the equations of a Frobenius algebra, it has to be a abelian groupoid, which is just a disjoint union of abelian groups. So if you have this map satisfying the algebraic conditions you want, this X is actually just a disjoint union of abelian groups. Okay, so we can now think of observables in this other setting, and they turn out to be these abelian groups. We can start to play with this. So that was a quick kind of tour of the monoidal approach and sort of how we think about observables there. And now we're going to take a look at the Topos approach. So what do we do here? Well, you start with a Hilbert space. You think of representing your physical system, and you want to consider the collections of this Holm set. This is the collection of all the bounded linear operators from H to itself, right? All the morphisms from H to H. And this has a lot of algebraic structures. So this is a C-star algebra. I'm sure some of you are familiar with this. So that means we have all these algebraic operations. We can add elements together. So if you have two of these morphisms, you can add them together pointwise. You can multiply them by composing them, and you can multiply by scalars as well. And you also have this involution of the star algebra. So you have all this algebraic structure here, and this represents your physical system, and in general this is a non-commutative algebra. So there are morphisms here which don't commute, and these might be morphisms that represent observables, and so this tells you something about quantum mechanics. And so in the Topos approach, they come up with this category here that I'm calling Hild-alge, and here the objects are the commutative subalgebras of this big C-star algebra. So this big C-star algebra represents your physical system, and it's non-commutative, but you want to look at just the commutative snapshots of that. Okay, and so these are kind of the classical snapshots of the quantum picture. And this kind of goes to Niels Bohr's doctrine of classical concepts, where reality is this big non-commutative thing, but the best you can do when you're sitting in the lab doing an experiment is that you get to see a classical slice, and then you have to have some way of putting all these together in a reasonable way. And so you can think of this as and my inclusions here are subalgebras, but you can think of this category as being the Poe-set of commutative subalgebras. So they're interested in this object, and then they're interested in sheaves of this kind. So Topos theory is very closely related to sheaves as well, if you know anything about this. and in particular define this spectral presheaf. So if this notation just looks the alien, then don't worry about it. All the spectral presheaf does is it takes an algebra, one of these commutative algebras, and it gives you the Gelfand spectrum. And the Gelfand spectrum you can characterize as all the morphisms from your algebra into the ground field. And so this is like a fundamental part of, if you study C-star algebras, this Gelfand spectrum is kind of fundamental. It's a very usual notion. Okay. And so I want to find some kind of connection between these Frobenius algebras and these commutative subalgebras. So if you have we're going to restrict to the finite dimensional case. If you have a finite dimensional Hilbert space, then you take one of these commutative subalgebras. It always decomposes in a very nice way. We have these subalgebras which are generated by these self-adjoint projectors, which are the primitive idempotents, if that means anything to you. And in particular, it's the spectrum that we just saw that encodes the information about how you decompose that algebra. So these projectors project onto some orthogonal subspaces, and this algebra A is maximal if and only if those are all one-dimensional subspaces. So there's no bigger algebra which this goes inside. So it's maximal if and only if it decomposes into one-dimensional algebra. So if we have all these projectors onto one-dimensional subspaces that are orthogonal, then we have an orthonormal basis, right? Because we have this collection of orthogonal subspaces, and so we can use that to specify an orthonormal basis. So we can see how a one-to-one correspondence here between the Frobenius algebras, which amount to specifying a basis, and a maximal subalgebra of this kind, which also corresponds to the basis. And in particular, it's the set-like elements of the Frobenius algebra which correspond with the elements of the spectrum. Okay, so this is the relationship. On the one hand, we've got the kind of monoidal approach to observables. On the right-hand side, we've got the Topos approach, and we see how they match up. But this is just in a very specific case. This is only talking about Hilbert spaces. So we want to understand this picture more generally. Now, we understand the left-hand side, the Frobenius algebras. We understand that in the most general terms, right? We can handle that fine. But this right-hand side, it's not clear maybe how to generalize this. This is very kind of specific to the classical formulation of quantum mechanics. We're talking about C-star algebras. So how do we really handle that? So what we've got to do is some real abstract nonsense now. If you have any symmetric monoidal category, we're going to show that you can actually recover a lot of the structure of the C-star algebra just from kind of really general structure. So you've got this symmetric monoidal category. We're also going to ask that it has byproducts. So byproduct is both a product and a co-product. So if you think the direct sum of vector spaces is an example of this. So Samson and Brodsky introduced this notion of abstract scalars, where you take the endomorphisms of the monoidal unit. And if this seems kind of completely obscure, if you have all the linear maps from the complex numbers to the complex numbers, this is actually isomorphic to the complex numbers. Okay, if these have to be linear. Okay, so. This is a generalization of this idea that you can encode actually the structure of the complex numbers by looking at this in a slightly different way. So Samson describes these abstract scalars, and they form a semi-ring, so a ring without negative numbers. Okay, so we're going to consider the Hom set, all the morphisms from X to X, and claims that we can add these. So with the byproducts, we get this natural diagonal map, and then we can compose them in parallel using the byproducts, and then we we reverse. And if you unpack this in the case of Hilbert spaces, this exactly matches up with adding these functions pointwise. So this is the direct generalization of that. We can multiply elements by composing them, because they're just morphisms, and these distribute in the way you want. And then we can also do abstract scalar multiplication. So we saw at the start that we have an isomorphism between the tensor product of the unit with x and x. So we do this isomorphism, and then we compose. My scalar is a morphism from I to I, and my f is a morphism from x to x. So we can compose them with another product, and then I do my isomorphism down the way again, and this corresponds to scalar multiplication in a very abstract way. And assuming that my category is a dagger category, I can also take involution of individual elements of this algebra. And so when you can go through and check that this actually gives you all the structure of a dagger with an algebra with a dagger involution. And so this is so with that in mind, I can define this new category, starting with my nodal category, and I pick some object. I can define the category of commutative dagger subalgebras of this big Hom set, and consider the poset of those commutative subalgebras. And also, I can look at the subcategory where I can impose an additional algebraic constraint of this von Neumann condition. You can characterize von Neumann algebras by this double commutant. So if you know what that is, then there it is, but if not, it's not too important. Okay, so the example, if you pick your monodal category to be Hilbert spaces, you get exactly what you want. You get the C-star algebras on H, and imposing this extra condition gives you, in fact, all the von Neumann algebras. So that this totally abstract stuff that I was just talking about, it does give you what you want in the Hilbert space case. And in fact, we can do further just in this really kind of abstract sense. So I have my scalars, which are the endomorphisms of the monoidal unit, and I can define this generalized Gelfand spectrum by just taking the homomorphisms from the algebra into the scalars. So again, this is on the nose, the Gelfand spectrum for the case of the Hilbert spaces. So what's the big idea is we start out with this monodal category, and we want to know, is there a relationship between the Frobenius algebras on a given object there, because these are the observables if you want to think about monodal categories, and these commutative subalgebras of the Hom set. These are the observables if you want to think about topos. And by the end of the talk, my sort of main kind of point here is to convince you that the answer is maybe. Right? So we saw what this story means in Hilbert spaces, and we see the connection. And so what I'm going to do is I'm going to work it out for a new category and show you that the connection is very similar. So what we have is a pattern emerging that I'd like to make into a more general statement. So we can consider the category of relations, right? So we already know a bit about the category of relations, so let's work it out for that. And so I can consider these commutative subalgebras of relations, and you can go through and just compute it, and you figure out what's the spectrum of one of these algebras, and if you know about algebra, it's the downward closed prime ideals. So maybe that's not so interesting. And so there's two results that I think really kind of will hopefully convince you that there is something deeper going on. So if I take one of these commutative subalgebras, it actually decomposes very nicely into this direct sum. And again, it's generated. Here the arrow means you have to take the downward closure. So you generate an algebra by these are projectors, so they're idempotent and they're self-adjoint, and and they satisfy this condition that they're also orthogonal. And moreover, if you work out the spectrum, it's the spectrum which encodes this information. The spectrum tells you how to decompose this algebra. And so this is strikingly similar to the decomposition for C-star algebras. I think this really isn't obvious. Like, this really surprised me when I worked it out. And the second result is that if you start with a Frobenius algebra, it determines one of these a maximal algebra here. So remember, in the case of Hilbert spaces, it was the maximal ones which corresponded with the Frobenius algebra. So this Frobenius algebra is a groupoid, so you get a kind of an indexed family of endomorphisms, and you just take the closure under all the algebraic operations that we pull out. And this gives you one of these. So we have this picture here. You start with the Frobenius algebra, you can build one of these maximal subalgebras. And moreover, again, it's set-like elements on this side which correspond to the elements of the spectrum. But with the Hilbert space case, this was kind of one-to-one. Here, this is not the case. There are maximal algebras that live on this side which didn't come from a Frobenius algebra. So it's a very similar picture, but we do start to see differences. So yeah, the big idea was, is there a relationship in general between these Frobenius algebras and these communities of subalgebras that we built? And now we have two solid examples where we kind of see this picture emerge. So at the moment we have these results which look quite similar for Hilbert spaces and for relations, but they really have completely different proofs. And so I'd like a more general theorem of which these are just kind of special cases. But there's more interesting things we can do as well. We can start to pull ideas from the monoidal approach over to the topos theory approach. So in the monoidal approach, you can handle ideas like non-locality very well. This has been kind of proved done. Whereas in the topos approach, contextuality is very easy to describe. And so can we use this as a way to translate the concepts of one to the other? And in particularly, so you can formulate the Koch-and-Specker theorem, which talks about non-contextuality, as a statement about the spectral presheaf. So the spectral presheaf for the Gaussian spectrum doesn't have any global sections. So this is equivalent to the statement of the Koch-and-Specker theorem. So we now have a spectral presheaf for REL. So we can ask the question: does this presheaf have global sections? And I suspect that it doesn't, but I haven't proven it yet. But it should be a way to make some statement about the contextuality there. And that's it. Thanks.
Thank you. Any short questions?
I wonder how you define the commutant of the
All right.
financial, because you mentioned that there's a double. How you define this in a categorical way?
Oh, well, you define it in the same algebraic way, because it's defined just in terms. You can define it on a monoid or even semigroup. So you just take the elements which commute with all the elements within it. You have a subset. The commutant of that set is just all the elements of the algebra which commute. Because I have my notion of multiplication is composition of morphisms. So my notion of multiplication is there. So I can just use the traditional algebraic.
Any more questions?
Do you have any idea what it is in REL that means you don't have this one-to-one correspondence?
I mean, I have examples which obviously don't. You can find the kind of the mapping which takes a groupoid to one of these algebras, and there are examples of algebras which don't live in the image of that. Even finite one, like really, you don't even have to have something weird. You can have a finite thing which just doesn't arise in this way.
Good. So let's thank you again.
One comes.